Hello, geometry students. Today we're going to be going over the Unit 9 review. So hopefully at this point you've done the rest of the Unit 9 packet, and you can follow along the video that I made for that if you need to. And before I go over the review, what I would like for you to do is just go through the review and answer all the questions that you think you could do on your own. So all the ones that you feel strongly that you can do confidently, go ahead and give those a try. And then you can watch the video to make sure you got the correct answers. If you need help with everything, that's fine. Just follow along, watch the video, and I'll explain as we go. Now, if you're able to do everything well on the review, then the test should be relatively simple because everything on the review will be on the test. Okay? And also, whatever I write down, you should be writing down. So let me go ahead and share my screen, and we'll go ahead and get started. So open up to the review on Unit 9, which starts on page 20. These first two probabilities, these first two definitions, I should say, are, I don't think they're in the packet quite like this, said so specifically. So here are the two definitions that they want for these two first two problems. So the theoretical probability is the likelihood of an event based on mathematical reasoning. So for example, what's the probability of getting heads on a coin flip? Well, I know the probability of getting heads is 1/2. I don't have to do any experimentation or anything. I could just come to that conclusion based on mathematical reasoning. So that would be a theoretical probability. That doesn't mean necessarily that doesn't mean theoretical probability is incorrect answer. It just means that it's not based on an experiment. And oftentimes theoretical probability is stronger than experimental probability, right? So like if I got let's say I flipped a coin 5 times and I got heads every time. Does that mean that it's 100% chance of heads? Well, obviously not. So the experiment is kind of misleading there. But theoretical probability, regardless of what happens, I know that the probability of getting heads is 1/2. Complement of an event is the combined probability of all other possible outcomes of the event. So for example, we've done ones like this before, but let's say the probability of, let's say you roll a die. What's the probability of rolling a 3, let's say? Well, the probability of rolling a 3 is 1 out of 6. So the probability of not rolling a 3 is 5 out of 6. Because there are 5 values that are not a 3 out of 6 total values. There's only one value that is a 3 out of 6. So it's the combined probability of all other possible outcomes. Question 3. A quality control inspector samples 600 LCD monitors and finds defects in 3 of them. What is the experimental probability that a monitor selected at random will have a defect? So here it's an experimental probability because the quality control inspector actually looked at 600 monitors and found 3 defective. So the probability of finding a defective is 3 out of 6,000. So we'd say the probability of defect is 3 out of 6,000. And you should always reduce this. So when you reduce a fraction, I'm looking for what can I divide both top and bottom by. In this case, I could divide both by 3. So that'll give me 1 over 2,000. And if you want it as a decimal, simply divide that. 1 divided by 2,000. So that gives me 0.0005. Now I'm happy if you leave it as a fraction, but just know sometimes on the test, you're going to see it as a fraction, sometimes as a decimal. So you should be able to do it either way. Number 4. What is the probability of rolling numbers that add to 6 when rolling 2 standard number cubes? What they mean is 2 dice. Use the chart to help you solve the problem. So we're looking for what's the probability of rolling a 6, basically. So I'm looking at these combinations of dice rolls, and I'm looking for any dice rolls that add up to 6. Well, you can see 5 and 1, those add up to 6. 4 and 2, 3 and 3, 2 and 4, 1 and 5. So there's 5 possible outcomes that add to 6. So we would say probability of rolling a 6 is 5 out of, now how many total are there? Well, this box is a 6 by 6 box. So there are 36 total different dice outcomes. So then there's 5 out of 36 is our probability there. If you want it as a decimal, it's 0.139 roughly. Okay. A jar contains 10 red marbles, 8 green marbles, 5 blue marbles, and 6 white marbles. What is the probability that a randomly selected marble is not red? So here we're doing the probability of not red. So this you can think of as a complement probability, but it doesn't make it any harder. We just want all the marbles that are not red over the total number of marbles. So how many marbles are there that are not red? Well, 8 plus 5 plus 6. So that's 19 marbles that are not red. Now, how many marbles are there in total? Well, there's 19 that are not red and 10 that are red. So there's 29 in total. If you want that as a decimal, 19 out of 29, 0.655. Again, I'm happy leaving it as a fraction as long as the fraction's reduced. So if you leave it as a fraction, I'm happy, but you should be able to know how to change it to decimal. Okay, for fullest understanding, you could write it as both. For question 6, this definition, you can find it on page 7, relative frequency. Okay, and we'll talk about what this means as we do some of the problems that involve relative frequency. But if you go to page 7 of the workbook, go ahead and find that definition there and copy it here. For number 7, probability distribution. So it shows the probability of each possible outcome. So we're going to see problems that work with this, and I'll explain it as we go. Question 8. The results of a survey of students' music preferences are organized in this frequency table. What is the relative frequency of preference for hip hop? So we're looking for a relative frequency for how many people like hip hop. So it's the same as asking what's the probability, given this survey, what's the probability that someone prefers hip hop? Well, you would just, it's the same as asking what's the probability that someone chose hip hop, which is 7 out of the total, right? So what's the total? 10 plus 7 plus 8 plus 5 plus 6 plus 4, 40. So the probability that someone chose hip hop is 7 out of 40. So 7 out of 40 people preferred hip hop. If you want it as a decimal, that's 0.175. Okay. Now you can use this table to find the relative frequency for all of these. And when you find all the relative frequencies, they should add up to 1. But you don't have to do that. A student conducts a probability experiment by tossing 3 coins, one after the other. Using the results below, what is the experimental probability that exactly 3 heads will occur in the next 3 tosses? So basically, we're looking at the relative frequency of 3 heads. So that's just this one right here. See, all these other ones have at least 1 tail in them. You see that? So this is the only instance of getting 3 heads. So there's 5. So the probability of getting heads, heads, heads from this experiment was 5 out of, what's this total here? So 5 plus 7 plus 9 plus 6 plus 2 plus 9 plus 10 plus 2. So there was a total of 50. They tried flipping 3 coins 50 times, and 5 of those times got heads, heads, heads. Reduce the fraction. Always reduce the fraction. If you want it as decimal, that's 0.1. If you want it as a percent, just move the decimal twice. So that would be 10%. Okay. 1 over 10 is the same as 0.1 is the same as 10%. So all these are all the correct answer. They're just different ways of writing it. In a recent competition, 50 archers shot 6 arrows each at a target. 3 archers hit no bullseye. 5 archers hit 1 bullseye, blah, 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 blah. Okay. What is the probability distribution for the numbers of bullseyes each archer hit? Fill in the probability row in the table below. I don't know why it says no. Anyway, so how many people got 0 bullseyes? Well, 3 archers out of the 50 archers hit the bullseye 0 times. 5 archers out of the 50 archers, or if you want to reduce it, 1 out of 10, they hit the bullseye. 5 archers hit the bullseye once. 7 archers hit the bullseye twice, so 7 out of 50. So 7 out of the 50 archers hit the bullseye twice. 7 archers out of the 50 hit the bullseye 3 times. 11 archers out of 50 hit the bullseye 4 times. 10 archers out of 50, which reduces down to 1/5. So 1/5 of the archers hit the bullseye 5 times. And 7 out of 50 archers hit the bullseye 6 times. Yep. These archers are quite good. For these 3 definitions, you can find their definitions on these pages. So fundamental counting principle can be found on page 12. For permutation, page 13, and for combination, also on page 13. The main things I want you to remember is that for a permutation, order matters. Order matters. For a combination, order does not matter. Okay. Again, for permutation, order matters. So this is like getting first, second, third, right? Getting first place is different than getting third, right? So that order matters. Combination, order doesn't matter. Okay. Order doesn't matter here. Okay. A deli offers a lunch special if you choose one from each of the following types of sandwiches, side items, and drink choices. How many different lunch specials are possible? So you're going to get to choose 1 sandwich, 1 side item, and 1 drink. Now, how many different lunch specials could you make here? Well, you would take however many different options you have for sandwich. So in this case, 1, 2, 3, 4, 5, 6. So you have 6 different options for sandwiches. You have 5 different options for a side item. And you have 6 different drinks to choose from. So the fundamental counting principle says we just multiply these together to get the total amount of different different outcomes we can have. So 6 times 5 times 6, which is 180. So there's 180 different lunches that you can make. Okay. You download 5 songs on your music player. If you play the songs using a random shuffle option, how many different ways can the sequence of songs be played? So the answer to this is basically, if you think about, there's 5 places to fill. There's 5 places to fill. So one of the songs can get played first, then the next song gets played second, then there'll be a third song, and I'm assuming there's no repeats. It doesn't say that, but it's basically saying how many different sequences of songs. It's kind of basically seems to me like it's saying that you can't have the same song repeat. So how many different songs could be the first song? Well, there are 5 different songs. So when you start up your music player, there are 5 different songs that could come up first. Now, once that first song is played, how many different songs could come up second? Well, once this first song has been already been playing, then there's only 4 songs that could come up as the second song. Similarly, after 2 of the songs have been played, there's only 3 options for the third song, only 2 options for the fourth song. And once all of these have been, once you've heard the first 4 songs, you already know what the 5th song is going to be. So this one doesn't have an option. There's only 1 option for it. Okay. And based on the fundamental counting principle, you just multiply those together to get the total number of possible sequences of these songs. So 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. So there's 120 different ways that these songs can be played. Now keep in mind, this is the same as 5 factorial, if you remember that. So 5 factorial, that means 5 times 4 times 3 times 2 times 1. Another way to think of it as 5 factorial is the number of ways of ordering 5 items, or putting in order 5 items. So same thing with any factorial. If you see like 7 factorial, that means how many different ways can I order 7 items? So how many different orders could I make using 7 items? That's 7 factorial. It'd be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. Number 16. The Environment Club is selecting a president, vice president, and treasurer. How many different ways can the officers be chosen from the 5 members? So you have 5 people, and you're choosing a president, a vice president, and treasurer. Are these positions the same, or are they different? Well, I would say these positions are different, right? Being chosen as president is different than being chosen as vice president. And these are both different than being chosen as treasurer. So in this case, I've got 3 spots to fill that are all different. And I've got 5 members. So let's say this first blank is for president. How many different people could be the president? Well, since you have 5 members on the club, there are 5 people that could possibly become the president. Once the president's chosen, how many different people could be vice president? Only 4, right? And once president and vice president have been selected, how many different people could be the treasurer? 3. All right. Based on the fundamental counting principle, you multiply those together to get the total number of ways that these positions can be filled. So 5 times 4 is 20. 20 times 3 is 60. So there's 60 different ways that we can fill these offices. Suppose that you choose 4 books to read on summer vacation from a list of 6 books. How many different combinations of the books are possible? Okay, well, I want to point out a distinct difference between number 16 and 17. 16, this one was a permutation. And the reason why is because order mattered, right? Being chosen as vice president is different than president. These are all different outcomes. But this is a combination. So if a book gets put onto the reading list, I spelled combination wrong. So if a book gets put onto the reading list, it doesn't matter if it was put first or second or third on the reading list. At least it doesn't seem like the order matters here, right? If a book is on the reading list, it's either on the reading list or it's not. There doesn't seem to be any significance about being put first or second or anything like that. So in this case, this is a combination. So order doesn't matter. So the way we're going to do this combination one is by using our combination formula, which is NC3 NCR equals N factorial over R factorial N minus R factorial. So in our case, n represents the total number of books we have to choose from. So in this case, 6. So in this one's case, we're going to have 6 doing a combination, and we're choosing 4 to go on the list. So 6 choose 4 combination. That's the way a lot of people like to think of combinations, is I'm choosing to be on the list or not. So that's why, and choosing also starts with a C, so it helps remember, right? So this would be 6 choose 4. And so the formula, based on the formula, this will be 6 factorial over 4 factorial and 6 minus 4 factorial. So this would be 6 factorial over 4 factorial times 6 minus 4. That's 2 factorial. So this would be 6 times 5 times, and I'm just going to put 4 factorial over, and then down here I'm just going to write 4 factorial times 2 factorial, and 2 factorial is just 2 times 1. So notice I have a 4 factorial on top of this fraction and a 4 factorial on the bottom. These can cancel. Simplifies my calculations by quite a bit. But if you're not comfortable like figuring out what cancels or how to do that, you could always just write it all out, multiply it out, 6 times 5 times 4 all the way down, and do the same on the bottom. 4 times 3 times 2 times 1 times 2 times 1, and then just divide, right? So on the top here, though, we have 6 times 5, which is 30, over 2 times 1, which is 2. So that's 15. So there's 15 different lists I can make for these books. Number 18, a college student is choosing 3 classes to take first, second, and third semester from 5 elective classes offered in his major. How many possible ways can the student schedule the 3 classes? Okay, so in this case, it seems as though order matters, right? First, second, third semester. So in my mind, order matters, at least from my reading of the question. So I would say this is a permutation. A permutation. So I've got, the way I think of permutations, you have 3 spots to fill, first, second, and third semester. And there are 5 elective courses. So there are 5 options for your first course. Once that's chosen, then you only have 4 options for your second semester course. And then once those 2 are chosen, you only have 3 choices for your third semester course. So 5 times 4 times 3, 5 times 4 is 20, 20 times 3 is 60. So there's 60 possible ways that you can schedule the 3 classes. Okay. You can't retake a course, right? Otherwise it won't count the second time. So they have to be unique courses. Okay, number 19. 3 pool balls are randomly chosen from a set numbered 1 to 10. What is the probability that the pool balls chosen are numbered 5, 7, and 9? Okay. So here, the way I like to think of this one is like, imagine you have, there's 10 balls, right? So imagine the bag has 10 balls, right? And they're either numbered 5, 7, or 9. These are the ones I want. And then all the other ones I don't. So I just imagine there's 10 in here in total, but I just imagine there's 7 that are blue, right? And then there are 3 that are red, right? Imagine the 3 red ones are the ones we want. These are the 5, 7, and 9. Now, it doesn't matter which order I pick them out, right? Because it doesn't say that the pool balls have to be chosen in that order. It just says I need to choose these ones. So if you choose if you grab out the 7 and then the 9 and then the 5, that's good. If you grab out the 9, then the 5, then the 7, that's good too. If you grab out the 5, then the 7, then the 9, that's good too, right? So any way that you pull those out, as long as you pull out these 3 specifically, that's good. So there might as well be like it might as well say there are 10 balls, 3 of them are red, the rest are blue. What's the probability of getting all 3 of the reds when we pull out 3 balls? Okay. So how do we calculate that probability? Okay. Well, what I would do is I would say, well, I'm going to pull out one of these balls. What's the probability I get a red one? Well, there's 3 red ones out of 10 total. Okay. Then I'm going to pull out a second pool ball. So imagine I pulled out one of the red ones. Good. And I put it to the side. Now how many pool balls are in there? Well, there's now only 2 red ones, and there's 9 in total down in the back. Then once I pulled out 2 red ones, now there's only 1 red one left inside out of 8 balls left in total. 3 times 2 times 1 is 6. 10 times 9 times 8 is 720. We can reduce that, which would be divide both top and bottom by 6 to reduce. I get 1 out of 120. So that would be the probability of getting the 5, the 7, and the 9, or getting the 3 red pool balls. Now, I know on the answer key, this isn't the same answer on the answer key, but this is actually the technically correct answer. So the answer key is wrong. And if your teacher wants to argue with me about it, I would be happy to tell them and show them and prove to them that they're wrong. Now, I also want to point out there's a question just like this on the test. And when you get to that question, I'll let you know none of the answer choices are correct because they don't do it this way. So since none of those answer choices are correct, I'm just going to give you the correct answer choice. And the correct answer choice will be the one that says 2.72. All right. So when you get to this question, that's with the pool balls or whatever on the test, just know that this is the correct answer. Okay. All right. Hope that made sense. If you have any additional questions, something that makes sense, you want me to explain something further, feel free to email me. My email is ttrigg@ofy.org. And good luck on the tests, guys. I'm sure you'll do great. See you next time.